representing the CU Boulder team. So can you guys see my screen?
Yes.
Okay, perfect. So we went with sort of a different approach than a lot of teams. So what we did was we used the IGSE algorithm as a starting point, and then we just used a simple random forest regression model to try to predict a correction factor for the IGSE algorithm. And then from there, we multiplied the correction factor by the IGSE prediction to get our predictions. So the first thing we did was we classified the waveforms. We used FFTs to do that, much like many of the other teams. And then what we tried to do was optimize the Steinmetz parameters because traditionally the parameters are extracted from the data sheets, but the data sheet, you only have a few select operating conditions, and even the Steinmetz parameters pulled from those operating conditions don't always match measured results. So what we did was we took advantage of the high volume of core loss data provided by the Princeton team for this challenge. And we found the Steinmetz parameters that would minimize the percent error just using the basic GSE equation. And so you can see here for an example material N87, those are pretty significantly different than what you would get just off of the data sheet. And we did end up constraining the Steinmetz parameters a little bit, just so that the model can better detect consistent patterns across materials. So it's not technically the true optimal Steinmetz parameters, but within a very reasonable range. And then we used a random forest regression to predict the multiplicative correction factor for the IGSE. The hyperparameters for our random forest regression were 100 estimators, so 100 decision trees, each with a max depth of 30. And one of the advantages of the random forest is that the bootstrapping nature reduces the likelihood of overfitting. So there's a few benefits to our model. We only use 24 scalar features as inputs, and most of those are just one-hot encodings. So it's really, the input features are very simple. We also generated one single model for all 15 materials because the material is only a one-hot encoded feature. So that does make the model very general because each prediction also uses the training from the other materials, and that sort of helps us and hurts us. I think it worsens performance on specific materials, but it does make the model very generalizable, and we'll see that a little bit later. The random forest regression is also very, very easy to train. There's no backpropagation, no iterative optimization. So that makes the model super easy to tweak if you get more data or you get more materials or something like that. And then the tree structure is also computationally simple. It's very fast to traverse because you're just doing a series of essentially inequalities. So some of the observations we discovered over the course of the challenge was, so after looking at results, it's clearly not the best specific model on any one material, as it's definitely outperformed by neural nets that are specifically trained for a given material. But we were pleased with its generality. By far, the best performance relative to the other teams was on material D, which is the material where you didn't have the trapezoidal, I think, wave shape. So that's good. And one of the interesting scenarios that we looked at was we wanted to test out how it would perform on a material that wasn't in the training set. So maybe one where you just have the data sheet. Most core data sheets only have core loss data for sinusoidal excitation. So we wanted to look at how does it perform if it's trained on the other 9 materials and then just the sinusoidal data for this new material. So we trained it using all the data for the other 9 materials, and then the sinusoidal data for the new material. And then we fed it all the data for the new material, including the trapezoidal and the triangular waveforms, to see if we could still significantly reduce error, even if we didn't have this wealth of of data that's provided by the MagNet challenge. And we were really pleased with the results of that, even though there is, decreased performance relative to when you give it all the data. Still, in almost all the material cases, you're getting down to around 10% average error. And that's, well under half what you're getting using the more traditional IGSE. So we were really pleased with the results of the scenario with the unknown materials. So in conclusion, our model's pretty simple, pretty fast. It requires a very low number of input features, and it has pretty decent general performance and good generality and performance on new materials, but is fairly easily outperformed by specific models that are like the neural network models that are trained just for a given material. And of course, we'd like to thank Dr. Chen and the team at Princeton for putting on this challenge. It's been very fun.
Yeah, great, Bailey. I want to applaud that. You guys the models are just great. It gives us a lot of difficulty in evaluating the model because like completely not trying to win the challenge, but shining on many other aspects. So the metrics designed for this challenge was not the right caliber to evaluate your model. I want to make it very, very clear. So for example, when we're looking at random forest, we know it's very simple, easy to train. Computing is very fast, but you have to use a lot of parameters, and a lot of parameters are not really using. You just store it, but you don't need to use it in a computing process. So that's like going against the way we evaluate. There's no right or wrong. It's just like when we design the rules, we think, oh, okay, maybe computing doesn't matter, parameters matter, but you can go with a different argument saying computing matters and parameters doesn't matter. So so that's why we think the method is very innovative and generalizable and has its own unique advantages. I would encourage you guys to keep pushing this forward, and MagNet challenge is MagNet challenge, and you guys' performance is great. The model size is big, but that doesn't mean that model is not a good model. It's just like the way we evaluate the model was designed geared towards more lower parameter, more computing versus less computing, more parameter. Yep, great. Any comments, questions from the audiences? Haran, Shukai? So,
yeah,
go
not
ahead.
really. I mean, not really question. It's very unique solutions, like using the random forest, and it's quite different from all of the other neural network models, I think. Yeah, it's a good approaching, I think.
So when you guys are selecting a strategy, what drives you towards random forest model?
Well, we wanted something that we would be able to use in the lab when designing magnetics, and we weren't sure that necessarily in that scenario we would be using the 10 materials here. So we wanted something that was pretty resistant to overfitting.
Okay.
It would produce that general model that would allow us to use it down the road.
I see. And did you consider other sort of data-driven approach beyond neural network? We know there are some other models.
Yeah, we looked at some other regressions that did not perform as well.
Okay. So what do you see as the risk of this approach? Like the downside of this approach, I can say, is you have to store a lot of parameters, and the parameters, it's very hard to get the physical meaning of those parameters as well, right? I guess for random forest. And do you think you said that this model is very generalizable. You're saying the structure are very generalizable, but the parameters for each material has to be retrained.
Yes. Yeah.
And then my question will be, for the model size that you have now, what will be the smallest data size you can use in order to train a proper model? Like 30 branches with 100 parameters. Like what will be your data requirements to get a reasonably good model?
In terms of like the number of samples?
Yes.
Yeah, I'm not sure about that. We haven't done a lot of testing with that specifically, but that's a good question.
I see. Yeah, I guess one interesting test will be just linearly scale down the side and see how does the accuracy drop. When does the accuracy drop significantly?
Yeah.
Yeah, great. Yeah, continuing these efforts. This, I guess, this is great. Very good, very good. Diversified methods. Like when we see this new neural network method, which is very different from other neural networks, is very, very exciting. Okay, great. I guess that's caused the end of today's town hall meeting, and we'll have 8 teams remaining for tomorrow. We'll see you tomorrow. Thanks, everyone.
Thank you.
Mingy.
Yep.
Okay. You said that we asked you from mail to get access to the videos. My supervisor couldn't make it, and he would like to see what the teams are doing.
Yeah.
So I just sent you a mail.
Yeah.
Okay,
so
perfect.
after tomorrow, we will compile the video. My plan is to segment the videos into teams, and then we can just share the link with you. It'll be stored in a folder, and then
Okay,
we
thank
can
you
share
very
the
much.
link with you. Yep.
Perfect.